Hello, Ezra's hallway. Hello, Ezra's shoulder. Jordan, how you doing this morning? Maybe Jordan can't hear me. Ezra does have a cool ceiling. It's true. So I have gotten behind and haven't had the chance to pop out you guys' chapter 3 topical videos yet. I'll have to catch up on those this weekend. So my plan is, instead of us going farther ahead in recitation and getting more out of sync with those, give me the chance to catch up by popping chapter 3 and hopefully chapter 4 out this weekend. And then we'll finish discussing our chapter 3 stuff on Monday. That will probably mean that we have to push our exam back by a couple of days, and that's fine. All right. We don't have any quizzes out, Ezra. So the quizzes are not behaving correctly for me in Canvas. Every time I try and fix them, I haven't been able to do it. So I may end up completely scrapping the idea of reading quizzes. I will show you something that will help you prepare for exams even more than Alex in lieu of reading quizzes, though. So let me share my screen for a second. Here, I want to show you exactly what you'll see. And of course, I have every module open right now. Ugh. So if you scroll down to the bottom of our Canvas front page, you will see that now you have exams to help you practice for all 3 of our in-class exams. And these practice exams are literally old versions of the exams that I've used for you guys, all right, for this exact class. So if you're thinking about the kinds of questions and the difficulties of questions that you might get asked, this is a really good place to start thinking about that. Now, if you don't know some of these questions, that's because we haven't covered quite everything yet from the chapters, all right? So that's not that big of a deal. We have talked about how many neutrons tin has if it's tin 118. Now remember, you're not going to be taking this exam in a vacuum. You will have a periodic table. So remember that. You should be able to look up what tin's atomic number is and then be able to figure out that because tin has an atomic number of 50, that must mean that 118 minus 50 is its number of neutrons. So 68 would be the right answer. All right. Anyway, these kinds of questions are the kinds of multiple choice questions that you're likely to be asked on the exam. And then there are also, halfway, so I'm just opening this file a different place so it's easier to see. There are also a number of different short answer or like essay kinds of questions. All right. So if you look at those, they're all things that we either have covered or will cover in our last little bit of discussion of chapter 3. So the last little bit of chapter 3 has this question in it, the quantum numbers. Note that you may not get this exact question this exact way on the exam. Matter of fact, you probably won't. But if you understand that question, that's the level of understanding I expect you to be able to answer questions about the quantum numbers. We talked about what moles are. So every once in a while, I do have students write a little explanation, because if you can explain something, then you really understand it well, if you can write about it. Some significant figures calculations. And then some calculations that have to do with numbers of moles. So we did some of those. These are all really fun kinds of practice problems, and they're very similar to the kinds of problems that you're likely to see on the exam. An essay question about light. So we definitely did lots of kinds of questions with those two equations that govern the behavior of light from the beginning of chapter 3. And then orbital diagrams, which is something that we'll cover at the end of chapter 3. So a lot of these questions already should look pretty familiar because they're similar to things that we've covered in class, in recitations, or in the first couple of chapters worth of topical videos. But the practice exam should be a great study tool for you guys. Part of the issue that I'm having with reading quizzes is for them to fill their purpose, I want them to be not too difficult. But if they're not too difficult, then maybe they're not hard enough to actually prepare you for the kinds of questions that you'll see on the exam. But if they're hard enough to prepare you for the kinds of questions that you'll see on the exam, then they also might be hard enough that you don't end up getting all the points on them, and that's not really their intention either. So I'm trying to figure out what to do with those. And this is a problem that I've had for my 160 classes ever since I've had to teach any parts of those online, like how to do reading quizzes and have them not be a punishment. So I may end up just throwing them out completely and making the homework or the labs worth a little bit more. Because I don't want to punish you guys. I want to help you, all right? Are the exams going to be timed? Ooh, that's a good question, Hannah. So here's what I know about how we do exams, all right? The exam will be given to you as a PDF file, very similar to this practice test. And in order for you to get that PDF file, you'll have to digitally sign your honor code to have access to it. So basically, like, don't have anybody else help you with the exam, agree to the conditions. So I'm still trying to decide what sources I'm going to allow you to use for the exam. In likelihood, because it's impossible to enforce exam security really well from a distance, it'll probably be open note, open book, all right, open periodic table. But because of that, I have to create questions in a way that those sources can't help you as much. In other words, I can't give you things like definitions on an exam that's open book, because you can just look up the definition and write it down word for word, and it doesn't mean that you've actually learned anything. So that's one thing that I'm still thinking about, is what do I want you guys to be allowed to use on the exam? It's actually a lot easier to write a test that's closed book than open book, because I can ask you some very basic questions that you should know without looking at any other materials. So how we enforce timing on the test, Hannah, is once you sign your honor code to get access to the test, that assignment starts a clock for you, all right? And then after that, I can see how long after that you submit your assignment to the inbox in Canvas to submit your assignment. So when you're finished taking the test, you'll turn it into a PDF file by taking pictures of all the pages and turning it into a PDF, and then you'll submit it to the Canvas inbox for the test. So I'll have a timestamp for when you open the test, and I'll have a timestamp for when you turn the test in, and it'll be like a 2-hour time block, maybe even like 2.5 hours to give you time to make your exam into a PDF. So I want you to have a little less than 2 hours total to work on the exam. And the exam will be open and available for you to use anytime from, like, say 8 or 9 in the morning until 11 or midnight. All right, so you'd have to start taking your exam sometime between 8 a.m. and let's say 10 p.m. to finish it by the time it closed. So you'll have a 2-hour time block and it's going to be monitored, but you can take your exam anytime that day that you want to. Does that make sense, Hannah? Okay, good. And if it didn't make sense, if you didn't get all the words that I just said, no big deal at all, because in the few days leading up to the exam, I'll post an announcement with the exam instructions so that you'll be prepared for it. All right, so you'll know exactly what you're doing before you begin working on the exam. The other thing is, on the day of the exam, I always clear my schedule so that I'm just sort of sitting around waiting for people to text me, because people always are going to have issues on exam day. So I'll be around if you are having trouble getting to a file, or if you're having trouble submitting your exam, any of those kinds of things, or if you have a question about a question that doesn't seem to make sense. I'm not going to promise that I can help you with that, but I might be able to clarify what I'm talking about a little bit or something. So I should be available on exam day basically the entire time the window is open for quick questions and things as well. All right. So I want it to seem as close to an in-person exam as possible, instead of just like, hey, I'm doing this all by myself and submitting it and we'll see what happens. Like I want it to seem as much like being together in class as possible. All right, so since we're going to chill on the end of chapter 3 until I pop the chapter 3 video content this weekend, our only job left over for today is to look at lab 3. So let's do that. Some of you will see grades already popping up for your lab 1. I graded a fair number of lab 1s last night, so the rest of those will be out this afternoon. You should be able to just open the file that you submitted and see my comments on it, just as if it were submitted on a piece of paper and I wrote on it and gave it back to you. So that's one of the nice things about grading in Canvas's iPad app, is I can grade it just as if it were a paper copy, which is really nice. Okay, so we're going to do 2 different experiments in Beyond Labs for this week. They're pretty short experiments, and they both have to do with atomic line spectra. So atomic emission is the same thing. So what do atoms emit when we excite them? They emit light at specific wavelengths. So that's where we get that atomic line spectrum from. So I'm going to the chemistry labs, and then under atomic theory, there's atomic emission spectrum. Oh, where did it go? Here we go. Dang it. Okay. So right when we open the lab, you'll already see hydrogen's emission spectrum. So you're supposed to describe it. What do you see? What are the colors? All right, so here's the emission spectrum. It's a little on the small side for you guys, but I see 1, 2, 3, 4 different lines in that spectrum. You still haven't received your textbook for the class. That's not great, Jordan, but I can help you with that. Okay. So it's not going to be a perfect one-to-one thing. It's not going to be the exact same textbook, but let me show you a place where you can find access to a textbook that is pretty much just as good as our textbook is. All right. And it's free. As a matter of fact, I've thought about changing over to this textbook more permanently. So if you would like another textbook that is open access, so I'm going to OpenStax Chemistry. So OpenStax is a collection of completely free resources available to college students trying to cut down on the cost of textbooks. And hold on a sec. There's also an OpenStax Chemistry Atoms First. There we go, Chemistry Atoms First. And the cool thing is, once you log in, you may not even have to log in. You should be able to just download a PDF of the entire book. All right, so that is a textbook that you can use to prepare. And if we look at chapter order in the textbook, I bet it's going to be very, what's happening here? I think the PDF isn't done loading yet, so it's going a little crazy. So if we look at the table of contents, yeah, very, very similar content. So chapter 1 is basic idea about measurements and uncertainty. All right. Chapter 2, atoms, molecules, and ions, is very similar to what we did for our treatment. And then chapter 3 is the electronic structure of atoms. So in terms of chapter order, this looks more or less like identical to the treatment that our textbook has, which means that you should be able to use this textbook and learn the same stuff at the same level. All right. So the writing isn't quite as good as our textbook, and the figures are a little bit dated in this book. But the cool thing is it's a PDF, all right, which means you can download it to any kind of e-reader and read it through there. The other cool thing is it's completely free. The other cool thing is if you want a paper copy of this textbook, there's actually a place on the OpenStax website to order a print copy, and it's basically going to cost as much as it costs for them to print it. All right. So a paperback version is $52. That's about as cheap as you can get for a textbook. And it's not the exact same textbook, but it has all the same stuff in it. And if you want to know who the real MVPs are, these two professors that led the effort to create these OpenStax chemistry resources, it is an incredible amount of work to write or even to curate a textbook. So these textbooks weren't just written by these two professors. Instead, what happens is there are a bunch of professors that get together and create resources and put them together to make a textbook to kind of decentralize the work a little bit, but somebody still has to be in charge of all of it. So these two were the ones in charge of all that effort, and they did it for free just so that students would have a really low cost option for a textbook. Isn't that awesome? Pretty amazing. They're also creating, if you're going to go on and take majors level organic chemistry next year, they're creating an organic chemistry OpenStax book as well. So I have contributed a little bit to that book, and hopefully it's going to be out sooner rather than later. But anyway, pretty amazing. Jordan, if you're going to use that book, can you do me a favor and tell me if you like it? And for any of you guys, if you want another resource with some extra problems or a different way of explaining some things, this book is really awesome, and I would love for more students to look at it to see if you think it is good enough in its current edition to to take the place of what we're using, because I would love to use an open source resource to save students money. I know that this book is not inexpensive. I'm using, I think, an old edition of it at this point, and that's good, but I would rather us have a completely free resource if it's possible. Sweet. Jordan, I appreciate that. So anyway, that'll help you until you get your book. All right. The other thing is all of our recitations are already uploaded up through Wednesdays. So those should help some as well. All right, so let's get back to our atomic emission spectrum. How many lines do you see? What are their colors? So that's pretty easy if you just look on the spectrometer to see what you see. So we can click on a switch to magnify just the visible part of the spectrum. So right now we can see a number of different wavelengths where we get light back, but if we magnify just the visible part of the spectrum, then it's pretty easy for us to see those 4 different lines, although one of them is pretty dim. Can you guys see this line right here? That one's pretty dim, but the other 3 are a lot easier to see. Now, the cool thing is if you look down here at the spectrum, you can actually see like basically the graphical readout of where that line shows up, and it shows up right underneath where it shows up here. So I can barely see this line at all, but I know it's there because the scale shows me it's there. So if you drag your cursor over a peak, come on, get out of the way. If you drag your cursor over one of the peaks in the graph, it will tell you what the wavelength in nanometers is of that peak. Oops, I just. So if you look at me dragging my cursor around, right down here is our X value. So if I move over to that peak, the X value or the wavelength for that peak, I'm trying to get right on top of it. This is much easier with a mouse than not using a mouse. So, oh crap. So I just zoomed in. That looks like about 410 nanometers to the nearest nanometer. So I zoomed all the way into between 410 and 411, and there's the peak right there. All right. So if we're going to the nearest nanometer, 410 nanometers is the wavelength, and you can always click back to visible and full and visible again, and it'll reset the graph. So it looks like this one is like close to 434. Yep, so 434. And then we can click and see right here, 486. Now, the other thing that's cool is when you zoom in, you can get a really nice view of the color of each of those spectral lines as well. Maybe I'll be able to see this one a little bit easier. Yeah, so it's a really, really dark purplish color, right? And then finally, if I click to, I didn't get good close enough there. So it's looking like 657-ish, somewhere around there. So another way that I can zoom in on just one little window is actually to click and drag across. So that's probably close enough for me here. It looks like 656 or 657, somewhere in that range to the nearest nanometer for that last line. So write those down, and then to do some calculations, very similar to the kinds of calculations you'll have to do on a test. You also have to solve for the correct frequencies of those four spectral lines. Remember that the spectral lines wavelengths are in nanometers, so to convert into frequencies in hertz or inverse seconds, you're going to have to convert these wavelengths into meters first to use that equation to convert into frequency. Do we think that the emission spectrum for an atom with 2 electrons instead of 1 will be much different? Well, I showed you helium's emission spectrum, so it is a lot different. That's not a great question, I suppose. All right, so we have to click and drag the electric field, place it on the stockroom counter, and then drag H2 gas sample and move it to the counter as well. All right, so basically, all right, so I took my apparatus to excite the atoms and I put it on the stockroom counter. I put my sample on the counter as well. Now I'm going to click into the stockroom and I'm going to go up to samples. And instead of hydrogen, I'm going to click on helium. So I've replaced my sample gas with helium now. And if I go back to the lab, I can put my helium sample and then my voltage across it, and you can see, yes, we do have a very, very different emission spectrum. So there's the full emission spectrum. Note that a lot of these lines are not in the visible region, all right? So remember, these are wavelengths all the way from 20 to 2120 nanometers. We're seeing peaks. The peaks that we can actually see are the ones between 400 and 700 nanometers. So when I switch my spectrum over to the visible part, that's where you can see those. Now it looks like there are lots of lines, but some of them are pretty low in intensity. So I can't remember exactly what we're supposed to do with these lines after we look at helium spectrum. I don't think we have to do all of them. All right, is it different from hydrogen? Okay, so anyway, tell me what you see in the helium emission spectrum. And then after that, we have to find the wavelength, frequency, and energy for the farthest right peak in the spectrum. So that's this peak right here. Remember, if we want to zoom in on that peak to get its wavelength a little bit more accurately, we can zoom by boxing around it. All right, so to the nearest nanometer, you can see in the x coordinate what our wavelength is. That's in nanometers. So we should be able to calculate the frequency and energy of that light that is coming out of our helium atom. And that's it. So do yourself a favor, and for fun, even though you only have to look at hydrogen and helium in this lab, take a minute and look at a couple of other samples. All right, it's really fun. So that's my high voltage apparatus. I took that off because I have to move the sample back. I go back into the stockroom. We have lots of different gaseous samples. Mercury is a really cool one. All right, I've never looked at some of the ones that are compounds instead. So don't bother because that mixes atomic emission spectrum from more than one kind of atom. But nitrogen is a pretty neat one, and mercury is a pretty neat one. So really, any of these that are just elemental substances are all pretty neat. Let's look at iodine. I haven't looked at that one in a long time. So now I have iodine in here. I'm going to go back to the lab. and place my iodine sample and my voltage. Whoa, crazy. All right. So that is just in the visible region of the spectrum. All right. There are lots and lots and lots of lines there. And let's look at mercury for just a second because it's not quite as complex. So part of the reason why mercury has, or why iodine has so many lines is because iodine is a very large atom, which means that as we start talking next week about how electrons are organized in iodine, iodine has lots and lots of allowed places for electrons to be outside the nucleus. So lots and lots of shells of electrons. And within those shells, there are lots and lots of subshells for iodine since it's such a big atom. So that's why there's so many lines, because there's lots of places where electrons are allowed to be outside iodine's nucleus. Let's look at mercury, and then we'll go on to the second lab. So mercury is not quite as cray-cray as iodine is, but still lots and lots of different lines in its spectrum. Remember that each of these lines represents an energy transition, all right? So an electron started at a higher energy level and fell to a lower energy level in the atom, and as a result, it released a photon of light. So all of these represent some difference in energy between places outside the nucleus where electrons are allowed to be in mercury. And then we'll look at the second lab, the Rydberg equation lab. So when you're finished in this lab space, you should be able to click up. Oh crap, I just destroyed it. That's not what I wanted to do. So I'm going to go to chemistry. And under atomic theory, the Rydberg equation lab should be down here. There we go. So we are back to hydrogen's emission spectrum. What are we going to do with it? We're going to do some different things with it this time. We're going to use the Rydberg equation to make some calculations about hydrogen spectrum. So we're going to magnify the visual part of the spectrum. You're going to write down wavelengths in nanometers for the 4 lines that you see, convert those to meters. And then after that, you're going to convert those into 1 over wavelengths in meters. All right. So 1 over wavelengths in meters is what you see on the left-hand side of this equation, which is why you're converting into inverse wavelengths over there in the right-hand column. It's asking you about the relationship between wavelength and energy. So remember, we derived the equation that the energy of a photon of light is equal to Planck's constant times the frequency. If we substitute in frequency that we solve for in C equals lambda nu, we end up getting that the energy of a photon of light is equal to Planck's constant times the speed of light over the light's wavelength. All right. So using this relationship, hc over wavelength is equal to energy. What can we say about the relationship between wavelength and energy? And by that, I mean, is it a direct relationship? As wavelength gets bigger, energy gets bigger. Is that true? Or is it an inverse relationship? As wavelength gets bigger, energy gets smaller. So that's what you have to tell me. And then you have to use the Rydberg equation to be able to figure out which of the lines corresponds for a transition from n equals 3 to n equals 2. So in the Rydberg equation, n sub f here is the place where the electron ends up. We know now that those are shells, all right? So the lower number is n final, and the higher number is n initial. And these numbers are just counting numbers, integers. So what these represent is the places outside the nucleus where the electron is allowed to be, the shells. And we just give those shells numbers for the sake of like giving them a name. So n equals 1 is the shell that is closest to the nucleus in hydrogen. And I'm going to draw a picture because you may not be able to figure that out without. So at least for hydrogen, we can think about the allowed places outside the nucleus as being just representative of shells. It gets more complicated than that for any atom that has more than one electron in it, but that's why we spend our time thinking about hydrogen, because it's an easy model to understand. So out of these 4 wavelengths, those are going to correspond to 4 different energies, all right? So one of those 4 lines is going to correspond to what happens when an electron starts in n equals 3 and falls back down to n equals 2, all right? So there's some difference in energy between those 2 shells. So it would make sense that if an electron fell from n equals 4 to n equals 2, that electron would release more energy because there's a larger difference between those 2 shells. An even larger energy difference exists between n equals 5 and n equals 2, and an even bigger energy difference than that exists between n equals 6 and n equals 2. So if you were trying to figure out which one of our 4 spectral lines corresponds to the transition from n equals 3 to n equals 2, it's going to be whichever one has the lowest energy. If you're trying to figure out which one of the 4 spectral lines corresponds to an electron falling from n equals 6 to n equals 2, it's going to be whichever one of those 4 spectral lines has the highest energy. All right? Probably easier to see that with a picture. Okay, so then you've got to fill in your results table. So if you had your n initial as 3 and your n final as 2, it would be 3 to 2. So then you would calculate your value of what's in the parentheses here for where n equals final is 2 and n initial is 3. So that would be 1/4 minus 1/9 would be what you have in here. And then you'd move your answer from the previous page, the 1 over wavelength, into that last column. So you can match up which of the lines in the spectrum shows up as each of these transitions. So this is supposed to teach us how we can use the Rydberg equation as the way to predict where those wavelengths for those 4 spectral lines in hydrogen's visible spectrum shows up. And the cool thing is we can use a spreadsheet to graph where 1 over our wavelength is our y-axis, and then what's in the parentheses here is our x-axis, because this is actually a linear form here, all right? So if this is y equals mx plus b, and b is 0, then in this case, y would be 1 over wavelength. X would be what we get when we put our integers into this parentheses. And if we graph those two, the slope of that line should be the Rydberg constant. All right. So you should be able to find the Rydberg constant on your own if you graph these data points in Excel. So let's do that really quick. And I'm going to use intentionally bad values in order to make sure that you can't copy me. How many of you guys, I'm going to stop sharing for a second because I need to get my graph, or I need to get Excel ready, and I also need to do some quick calculations. How many of you guys have used Excel to make graphs before? All right, so for those of you who I can't see on camera, can you give me like a thumbs up or say in the chat? I just want to know what I'm working with here. If you haven't, that's fine. I can teach you. Hannah says yes. All right, and then Jonathan says I haven't. That's fine. It's totally fine. And not the kind of fine where we're a dog sitting in the middle of a restaurant on fire and it's fine. Like, it's actually fine. I can teach you how to do that. Ellie, you've never seen that comic strip before? There's a comic strip that's like it's one that gets referenced a lot right now because everything is crazy. But anyway, there's like this dog sitting in the middle of a restaurant and everything is on fire around the dog, and the dog's eyes are like the size of saucers. It's like, it's fine, it's fine. So it's basically like, I'm just gonna ignore everything that's wrong around me. No, it's not that kind of fine. It's really fine in this case. All right, I can teach you how to use Excel. It's not hard, but I have to be able to make a data set. As a matter of fact, it might be more fun for us to make a fake data set and then you can put in your data into Excel, but I'll make a fake data set for right now. As a matter of fact, I already have a fake data set. It's not a fake data set, it's a data set for another lab I was doing with students. So let's imagine that these were our 1 over frequency, or sorry, 1 over wavelength. Oh wait, those would be our, hold on a second. I need to look back. One over wavelength corresponds to Y, and this corresponds to X. Okay. So in order to make a graph in Excel, the easiest way to set it up is if we have the column that is our X data, our first column that we're going to highlight, and the column that's our Y data be the second column that we're going to highlight.
We can't see your screen.
What? I can fix that. So this is completely fake data. These are not real values that you would get by substituting in integers into the Rydberg expression. These are not real wavelengths in the hydrogen spectrum, but here is where you're going to put your X values that you calculate, and here's where you put your Y values that you calculate. And then in order for us to get a plot of those, I'm going to highlight all of the data. And by the way, all of you have free access to the Microsoft suite of Office products. So because you're enrolled in a college, which is really great. I mean, they're not perfect, but they're pretty good. So I'm going to go to Insert. And over here in the charts, the kind of chart that we want to insert is a scatter plot. So I can click and hold, and there are different kinds of scatter plots. The scatter plot that I want to use is one where I just see the data points themselves and nothing else. We can change our chart title. We're using this graph to solve for the Rydberg constant, and because this line, the slope of this line is the Rydberg constant, I guess that's a descriptive enough title. So from here, we can also add titles to the axes. So our horizontal axis is what we solve for inside that parentheses. So this isn't a clean unit. What do I want to call this? And then for my vertical axis title, inverse wavelength in units of inverse meters is what we're after. Okay, so finally, how do we use Excel to solve for the slope of this line? Because we certainly can. All right, and there's more things I can teach you about Excel. Like, for example, for some reason, Excel really likes to waste space when it creates line graphs. Notice that all of this space down here is just dead space. It doesn't have any points in it. So we could start our Y at 1500 instead of 0, and it would be a nicer looking graph. So I'm going to right click on that axis and go to Format Axis. And I'm going to start my graph at 1500 instead of 0. And I just hit enter. And now I have a graph that looks a lot cleaner because there's not as much wasted space. So anyway, you can play with and like customize the axes to show what you want out of the graph. But importantly, we need to be able to use Excel to solve for the slope of a line through a linear data set. So here's how we do it. It's going to be a little different for people on Apple computers because there's no right click, left click, but on a PC, I right click on this data point and then go to add trend line. So what Excel does is it looks at that data set and says, well, I think that's a linear data set. So it picks linear as the type of graph. And then after that, what we can do is we can display the equation of that line on our chart. So there's our equation of the line in the form y equals mx plus b. So if we had plotted our Rydberg data in the x-axis and 1 over wavelength in the y-axis, that m, that slope value, would be the value of the Rydberg constant that we would have. Christina, I saw that you were talking, but I didn't hear anything. So were you muted, or did you have something you need to ask?
I wasn't talking.
Okay.
It was probably just my thing moving.
That's fine. So the way that you can put that data into your lab, I would appreciate if you would actually show me the graph that you create in Excel for this. And the way that you can do that is in Excel. I'm coming back because I know I turned screen sharing off, which was dumb. In Excel, once you get your graph the way you like it, and that you have the equation on the graph itself, so I can see that you did the calculation, you can literally just click on your graph to, oh man, come on. Click on your graph to highlight it, and then Control-C to copy it. And then after that, you can paste it in as a last page into your PDF. So you could paste it into a Word document, or just paste it in as a last page in your PDF, so that I know that you did this calculation to get the Rydberg constant. So here's a Word document, and I've already Control-C'd from Excel. I can Control-V and just paste it right into a document. It's a little hard to paste into a PDF directly, but some apps will let you do that. It's probably easier if you just add one extra page to the last page of your lab and just throw this in on the last page for me. From there, you're going to compare your value of the Rydberg constant from your graph to the accepted value, and then calculate a percent error. If your percent error is more than about 5%, you've done something wrong. All right. It should be really, really close. People normally get great data for this. So neither one of these labs should take that long. I would expect that the first lab is going to take you all of about 20 minutes, and this one no more than maybe a half hour or so. If you're not familiar with Excel, it may take you a while to get to the place where you can get this graph the way you need it to look. If you're working on it over the weekend and you get stuck, don't worry about it too much. Just pop into my office hours next week and I'll help walk you through it. All right. Excel is something that it takes time to get comfortable with, but I make my students do some labs where they're making graphs in Excel, because Excel in the end, if you know how to use it well, actually makes your life like a ton easier. And it's very useful, not just for a chemistry class, but for math classes. If you ever have to do statistics, Excel has lots of tools that can help you with that. It's a really useful program. So I want you to at least experience using it some, because it's not something that we're just doing because we are using a tool that's not as good as what chemists really use. Real chemists use Excel to treat their data all the time. Any more questions about either of the two labs for today? All right, so over the weekend, I'll get caught up with our little topical videos. And on Monday, we'll finish talking about chapter 3. So the stuff that we have left to cover for chapter 3 is, I've given you all the data about the experiments that went into the quantum mechanical model. Now we actually have to talk about what the quantum mechanical model teaches us about where those electrons can be outside of the atom. So we're going to learn about the quantum numbers and also about electron configuration. So those are the things that are coming up for the end of chapter 3. And if I can figure out a way to do reading quizzes without them being punitive, I'll do it. And if I can't figure it out, then the reading quiz points, I'll let you know where those go. All right. Any other questions? Yes. Who's this? Is that Hannah?
Really dumb, but are you? Yeah. But are you actually going to be publishing this video on Canvas as well?
This video?
Yes. The recording.
Absolutely. Yeah. It's
Okay.
going up on Canvas.
Okay.
So if you're wondering about where the lab videos go up, let me show you really quick, okay? So on Canvas.
I'm able to find some, but I can't find others. Also, your screen, we can't see your screen.
Thank you for reminding me. All right. I'm sharing my screen again. Okay. So here is everything that you will see. So the class meeting recordings are normally our Monday and Wednesday recordings. All right. And then if you're looking for one of our lab tutorials, here are where we have our Friday recordings. So you can see that I've replaced the generic lab tutorials. So I've done tutorials for all these labs for previous classes. But if you want to look at when we did them together, so after today, after this video finishes processing in YouTube, I'll be able to publish it, and I'll replace this generic tutorial video from last year with the one from today. Does that make sense?
Yeah. Thank you.
You're welcome. All right, if you guys don't have any more questions, I'll get us all caught up over the weekend, and we'll finish up talking about chapter 3 and begin talking about chapter 4 next week. So have a wonderful weekend, okay? Jordan, are you good with that OpenStax book? Will that help you out some?
Yes, I was looking at it while you were talking.
Okay, good. And honestly, like if you have any kind of an e-reader, that's probably the easiest way, because then you can just like scroll through pages, you know, with your hand. But if you don't, you can read it on a screen too, and it'll be fine. All right.
Okay.
So in terms of having a textbook that's very similar to ours, that's the best I got for you right now.
Okay, thank you so much.
You're welcome. Have a good weekend.